Hi, everyone. My name is Alexey Peshkovsky. I am President and Chief Scientific Officer of Industrial Sonomechanics. Our company works with nanoformulations, mainly for drug delivery in the pharmaceutical industry and the cannabis industry. We develop and distribute ultrasonic equipment, scalable, high-intensity ultrasonic equipment that is used to produce nanoformulations, and we also develop formulations to accompany the equipment, thereby enabling our clients to produce their own water-soluble formulations of various bioactives, including cannabis, active pharmaceutical ingredients, things like this. I will talk about water-soluble cannabinoids and other bioactives, why they're interesting, and how you could make your own. All right. Cannabis is an interesting bioactive. It's consumed in a variety of ways. Everyone knows that you can smoke it or vape it or dab it, so using your lungs. You could consume it as an edible, so oral digestive route. You could put it into your bloodstream through a mucous membrane, let's say sublingual absorption or intranasal, even rectal exists. Or it could be a transdermal type application where it goes into the bloodstream through the skin. Now, all these different methods of delivering cannabis into the bloodstream coexist, and neither of them is perfect. Each one has advantages and disadvantages. For example, pulmonary delivery is very quick. It's fairly predictable. However, it's kind of harsh because you have to use your lungs, and not everybody likes to do that. It's also not particularly safe. If the formulation is incorrectly prepared, it could be a problem. You could poison yourself. There's been some cases, for example, people added vitamin E to their vape juice and had a serious health problem. I think several people died even. Now, oral digestive is much safer because you have the defenses that your digestive system just has naturally. However, that method is very slow and it's unpredictable. It depends on a lot of things: what you ate, whether you ate or not, your specific metabolism, things like that. So, serious disadvantages there. Also, it's slow and it's extremely long after it does come in. We'll talk about it a little bit later and the reasons for why this happens. Now, transmucosal is difficult because what you put under your tongue doesn't necessarily stay under your tongue. Typically, you swallow it, so it crosses over into oral digestive. In general, that makes it unpredictable. It's also not particularly efficient, although intranasal is more efficient, but not particularly convenient. Rectal is not very high on my list of social activities, I would say. So disadvantages there as well. Transdermal is very inefficient. Not a lot gets into the bloodstream through your skin. So question is, why are all these methods there? Why isn't there one good method that everyone would use? Are there examples of other bioactives that have a method of delivery that works for everyone? Well, alcohol. Alcohol is a water-soluble bioactive, and you could vape it. You could figure out a different method of delivery for it, but nobody does that because you could just have a drink and it acts predictably, reproducibly. You know what a glass of wine will do. You know when it will work. Whether you ate or you didn't eat makes a difference, but most people know what the difference will be, and there are no surprises. It doesn't hit you 2 hours later. So the argument that I want to make in this presentation is that if you could make bioactives that don't dissolve in water like alcohol does, if you could make them behave as if they were water soluble for the relevant intents and purposes of drug delivery, then you likely wouldn't need to have all these methods. You could just have a drink. You could just make a beverage or an equivalent of a beverage from this and deliver it that way. Now, skipping way ahead, I can show you that it is possible. You could make liquid or solid, powdered, translucent, water-soluble nanoemulsions that, once added to water, go mix very homogeneously with the water, become transparent, and behave as if they were water-soluble. Very technically speaking, they're not water-soluble, but they behave as if they were, and it's basically the same thing for the purpose of drug delivery. Now, to understand the basic theory of how those are made, we have to talk about what a surfactant is. So oil and water don't mix. You can stir them together vigorously, and as soon as you're done stirring, they will start separating, and eventually oil will, typically the density of oil is lower than that of water, and so it'll float, go to the top and form a separate layer. And that's because water molecules like each other a lot more than they like oil. They stick to each other and they expunge the oil. So if you disperse the oil throughout water, water will push it away, and to minimize the common surface area, it will simply push it to the top, because it's less dense and will have a minimal interface between them. Now, a surfactant is a type of molecule that has a part that dissolves in water and another part that dissolves in oil. This is, schematically speaking, a surfactant. So this oval part is a head. It's a, loosely speaking, a sugar derivative. And this type of molecule, if it were by itself, dissolves in water. This is a tail, which is an oil. It's basically a paraffin oil. Now, when you connect them to each other covalently, so it becomes a single molecule, it forms this type of entity with the heads that like water and with the tails that like oil. Now, schematically, let's represent it like this. And now let's take a situation where you have oil and water. Oil's on top, water's on the bottom, and you let surfactant into this arrangement. The surfactant molecules will naturally arrange themselves like so, with the hydrophilic, meaning water-compatible, water-loving heads in the water, and with hydrophobic, meaning water-hating, typically oil-soluble, tails pointing into the oil. So now look at this situation from the water's perspective. Water's happy. It looks at the interface, and instead of seeing the oil, it sees these friendly heads, which fill the surface. The oil, looking down, instead of seeing water, sees the friendly tails. So now you've basically relaxed the interface. Now you can do things with this mixture, and there are several things you can do. You can create a variety of formulations from it. Sorry, I guess I wasn't clicking on. Yeah. All right. So let me get to this. And now, okay. So you can make a variety of formulations. The first one I'm going to mention is a macroemulsion. Macroemulsion is a drop of oil that has surfactant on the surface, with the heads pointing out, with the tails pointing in. So the tails are in contact with the oil, the heads are in contact with the water that's outside, and then you have a lot of these drops that are dispersed throughout the liquid. Now, when these drops are larger than 1 micron, the right name for this is emulsion or macroemulsion, and it's a formulation that is somewhat stable, semi-stable, but ultimately will separate in a matter of sometimes minutes, sometimes hours, maybe days if you're lucky. They are typically made with vigorous stirring or rotor-stator homogenizers. Now, these formulations also don't really do much for the bioavailability. They don't improve it much, and they don't really shorten the onset of action, which is what you want from trying to make things appear to be water-soluble, okay? So we're not going to consider these formulations further, but they exist typically when people try to make nanoemulsions and they don't do it very well. They end up with kind of a pre-nanoemulsion situation, which is not stable, but temporarily looks like maybe you got the oil to mix into the water. Another typical formulation is a microemulsion, also called micellar suspension, also called self-emulsified system, sometimes SNEDs, for example. Self-emulsified drug delivery system, something like that. This type of formulation was used by the pharma companies up until about 20 years ago, almost exclusively. And that's because it leads to good results. You can effectively solubilize oils with bioactives in water and get decent results, get good bioavailability improvements, onset of action reduction. However, the problem with these formulations is that in order to make them, you have to use a lot of surfactant. And typically the surfactant is synthetic, harsh, probably bitter tasting, soapy tasting, probably with some limitations on the amount you can use on the maximum concentrations. But, for the pharma industry, for people with a disease, maybe surfactant is not the worst thing. If they need chemotherapy and the only way you can get it is by ingesting extra surfactant, well, okay. However, for the beverage industry where you don't have to, you just want to have a pleasant beverage, it's a limitation, a big limitation. Also, these things are stable. However, if something changes like pH, they can easily separate. So this is what people used to use, but almost, well, I shouldn't say they don't use it anymore, but less and less with time. And that's because there are alternatives now that I'll mention. The next formulation I wanted to mention is liposomal suspension. Liposomes are very interesting, very useful in the pharma industry and in the beverage industry, but they're not really appropriate for bioactives that dissolve in oil, such as cannabis extracts. And that's because liposomes have water on the inside. Then they have a lipid bilayer. They have surfactant with heads pointing in and also out. There are two layers of them. And then there is a layer of oil where you could put cannabinoids, but that layer is pretty thin, so the loading factor is insignificant. And then there's water on the outside. So liposomes, the word liposomes is used a lot because it sounds good or for whatever other reason. But typically when people say liposomal suspension or liposomes in combination with cannabis, they typically mean nanoemulsion. So liposomes are used for water-soluble formulations to slow them down. It's kind of the inverse problem. Like you can put vitamin C on the inside here and slow down its release because otherwise it's too fast. Now, nanoemulsion. Nanoemulsion seems to be the best of all of these options. And that's because, like microemulsions, it consists of very small droplets. It's a stable formulation. Now, microemulsions are thermodynamically stable, meaning they will remain stable indefinitely. And they tend to self-form, which is why it's called self-emulsified system. Nanoemulsions require ultrasonic equipment to be formed, but they are also stable once formed, and the stability is called kinetic stability. So they will remain stable for years if they're made properly. They also require surfactants. However, the types of surfactants that can be used with nanoemulsions are much milder, greener, and you can use much, much smaller amounts of surfactants because you don't use surfactants to to push the process forward to the formation of these droplets. You form the droplets with equipment, which I'll talk about next, and the function of the surfactants is only to maintain what you've made. But in microemulsions, the surfactants that you've used to make these droplets will always remain with the product. Conversely, ultrasonic energy that you're putting into the formation of nanoemulsions, once you turn the equipment off, is no longer with the product. So you end up with much cleaner, much milder tasting, much healthier, greener formulations that way. A closer look into nanoemulsions. So small droplets, ideally 20 to 40 nanometers in size. They will have oil on the inside, surfactant on the surface, and water on the outside. Typically, the droplets should be somewhat similar in size between each other, and they comprise a carrier oil, that's the inside here, a bioactive, let's say a cannabis extract that is dissolved in the oil, surfactants on the surface, water, which is the outside. Now, if you replace water with something similar to water in its properties, but that happens to be solid at room temperature, let's say, loosely speaking, a sugar derivative, then this whole formulation could be a solid and you can grind it into a powder, thereby making a water-soluble bioactive powder. Preservatives, typically, if it's a liquid formulation, you want some preservatives in there because fungus likes this stuff just like we like it. And for this to qualify as a nanoemulsion, ideally the droplets should be below 250 nanometers. Now, if the droplets are below 100 nanometers, the formulation becomes translucent, which gives you additional advantages for the delivery of these formulations, which I'll mention in a bit. Ideally, the droplets should be between 20 and 40 nanometers in size. Now, it's important to point out that every once in a while it comes up that people perceive nanoemulsions as something potentially dangerous, and it should be addressed. The word nanotechnology is scary to some people, and it's important to mention that the terminology is somewhat new, but it doesn't mean that nanoparticles, specifically nanoemulsion particles, are new. For example, English breakfast tea is a nanoemulsion, 25 nanometer droplet size. McDonald's coffee is a nanoemulsion. Our blood, our gastric fluids, beer, milk, most beverages have nanoparticles in them. On the other hand, there are lots of novel nanoparticles, metal oxides, carbon nanotubes, buckyballs, things like that, that the nanoparticles themselves are new and not very well known. And so scrutiny is required for those, but it doesn't mean automatically that anything that has a nanoparticle in it will be dangerous. Now, you can create nanoemulsions with nanoparticles that are similar to what I just shown. So a typical CBD extract nanoemulsion has 26 nanometer droplet size. This is what it looks like. It's a translucent formulation. You can see the dropper through here. And this is the droplet size distribution for it. You can create solid versions of these formulations. For example, this is a CBD nanoemulsion powder, 35 approximately nanometer droplet size. You can do the same with other cannabinoids, and you can do the same with some other bioactives. For example, this is a it's not playing from the beginning, but this is a kratom extract, water-soluble mitragynine powder. You can see on the left is a water-soluble extract, on the right is a typical traditional extract. So once you do the conversion, you can see how the water-soluble version dissolves and the regular extract doesn't. It floats, stays on top. Now, being water soluble gives it lots of interesting properties, and we'll get into this next. This is a study, it's a published study on cyclosporin that shows the relationship between the droplet size and the blood intensity, basically the efficiency of delivery. You can say bioavailability, or peak concentration in the bloodstream in this case, really. At the bottom here, you have 400 nanometers. So this is a macroemulsion. And then about up here, it's 150. And then you can see that once you cross the threshold of 100 nanometers, there's a jump. And then everything that is below 100 nanometers, this is 60. Then there is triangles are 40. The black dot is 25. So 41 and 25 are up here. The rest is sort of also up here. And then there's a big jump when you cross 100 nanometers. And I will explain why that happens. Now, this is our data recently collected from delta-8 THC, liquid and powdered nanoemulsions in comparison with MCT oil solution for the same concentration. This is a preclinical trial. The main conclusion of this trial was that both liquid and powdered nanoemulsions very significantly outperform MCT oil solutions that mimic edibles, typical edibles, gummies, and things like that, especially within particular windows of interest. We were particularly interested in what happens within the first hour and within the first 4 hours post-administration, because this is typically what you would want when you would want a cannabis formulation to give you effects. You would want it not 4 hours later, but hopefully within the first 4 hours, and very hopefully within the first 1 hour, like alcohol would. So within the first hour, liquids outperformed edible equivalent by a factor of 16 times greater delivery into the bloodstream, and the powders by a factor of basically 19. Within the first 4 hours, liquids were better by a factor of 4, and powders by a factor of 3.5. Now, this was a result that we expected, although we didn't expect that much of a difference. But one unexpected result here was that liquid and powdered nanoformulations were very similar to each other in performance, while the liquid had 27 nanometer particles and the solid had 170 nanometer particles. So in the previous slide, we saw that that should have been different, but it wasn't. And we're going to study this further, but the theory that we have is that when we make solid nanoemulsion powders, we use a technique that prevents the bitterness. It somewhat masks the bitterness by adding side chains to the droplets that make the droplets kind of hairy, let's say, and that keeps them somewhat at a distance from the taste buds, and so they're not as bioavailable to the taste buds while they're in the mouth. Once they are swallowed, they reach the small intestine, where they're clipped off really quickly. And so it's possible that the actual droplets that are responsible for the efficiency of drug delivery are much smaller than they appear to be. When we measure them with the hair, so to speak. And when they're acting on you, they have the hair clipped off. There are ways to tell which it is, and that's what we're going to study next. This is human data for self-reported high for nanoemulsions, one nanoemulsion compared with an edible equivalent, MCT oil solution of the same dose, taken on a full stomach and an empty stomach. So the green line is empty stomach. You can see that the onset time is in minutes. In something like 40 minutes, it's at the top, then it stays flat, and then after 4 hours, it's gone. On a full stomach, it's a little bit delayed, it's a little bit higher. but it's in principle the same shape. Now, the blue line is an edible equivalent on a full stomach. You can see that for 2 hours, there's practically nothing. Then it comes in. As most people know, if you consume an edible on a full stomach, it'll hit you, but 3 hours later, right? And so that's what happens. And then it has a very long tail. Interestingly, on an empty stomach, if you take an edible, it tries to come in a little bit earlier, but then it can't quite do it. And as most people know, on an empty stomach, edibles don't hit you very much. However, it barely came in and it was going down, and we allowed people to eat. And it turns out that the stuff is still there waiting for some food to help it along. And so it came in after we allowed people to eat. There's an explanation for why this happens. And that is because when you consume oils, for example, triglycerides, or things that dissolve in triglycerides, because they're not water soluble, when you swallow them, they arrive in your small intestine as kind of like a blob, like a big drop of oil. And then lipases and locally produced surfactants, bile salts and phospholipids, surround this big drop, and lipases clip fatty acids from triglyceride chains, basically releasing free fatty acids. And then together with the locally produced surfactants, these free fatty acids assemble themselves into mixed micelles, similar to micellar suspensions I mentioned in the beginning of this talk. Now, these micellar suspensions consist of small droplets of about 10 to 30 nanometers in size. And these droplets will attract cannabis oils, cannabis extracts into their interior. And so they are used as transport. So they will be transported across the bulk of the water in the small intestine, and especially across the unstirred aqueous layer, which is a mucus layer that lines the inner surface of your small intestine, which oils can't cross because they're not water soluble, but these very small droplets can. And then they will fit into these small protrusions on the inside of the enterocyte cells, which are absorption cells. In order to absorb themselves efficiently, they have to fit in between these little hairy structures. They're called villi, microvilli. So they will fit in between the microvilli and become absorbed. Now, the distance between these microvilli and the diameter of each microvilli is about 100 nanometers, which likely explains why, when the droplets are smaller than 100 nanometers, the efficiency of absorption goes up. Now, the punchline to this is that a nanoemulsion is basically the same suspension of very similar droplets that is ready to go and doesn't require this lengthy process to occur in your small intestine. So when you drink a beverage based on a nanoemulsion, it's ready to go. That's why it acts more like alcohol that doesn't require any of this, that can travel through the unstirred aqueous layer and get absorbed. The same thing happens with cannabinoids that are formulated as nanoemulsions, because the size of the droplets and their behavior is identical. To make these, you need basically two things. You need ultrasonic equipment. Ultrasonic equipment uses an ultrasonic horn that you just saw in the beginning of this video that vibrates in the liquid and creates these vacuum bubbles. Vacuum bubbles grow to a critical size and then they implode, creating microjets. So what you see now is a white cloud of these vacuum bubbles, and the vacuum bubbles are formed and collapsed 20,000 times a second, 20 kilohertz frequency of oscillation of the tip of this horn. And the result is a very strong, very small scale microjet that hits a surrounding drop of oil and breaks it into much smaller pieces and continues to hit them until they reach a minimal size. This equipment typically is used in the flow-through mode when you're producing quantities that are other than laboratory experiment type quantities. So when you're producing it as a product, typically use a flow-through recirculating arrangement shown in this schematic. This is a typical bench scale ultrasonic system with a tank where you do your premix, and then you pump it through this reactor chamber where cavitation occurs, and it recirculates until it's finished. Now, these are three examples of ultrasonic processors: laboratory, bench scale, and industrial scale. They all produce the same results, but at different rates. I'll talk about them a little bit more in a minute. And then the other side of the puzzle is the formulation, surfactants and carrier oils and all that. And so good examples of those are nanostabilizer LT, which leads to translucent liquid nanoemulsions. It's an all-in-one formulation. Or nanostabilizer LSO, which is a powdered formulation that you can use to make powders. I'll expand on that in the next couple of slides. One thing you also need is drying equipment if you're going to be making a powder, because in the beginning with nanostabilizer LSO, you'd be making a liquid nanoemulsion, which you can then dry. For example, you can spray dry it, or there are other drying techniques, freeze dry it and whatnot, and then grind it into a powder. A very important thing to mention is that when you scale up ultrasonic equipment, you must make sure that the ultrasonic amplitude is maintained at the same high level that you used in the laboratory. Unfortunately, with most conventional systems, you can create high amplitudes on the small scale, but when you bring it to the industrial scale, the amplitude, you can see the sinusoid is much smaller, is not maintained. The power could go up, but the amplitude goes down, and that's the intensity that you require for making small droplets. And so if the intensity is not there, you will not be making the same quality nanoemulsion. So it's very important when you scale up to make sure that the amplitude is maintained, and this could be done with something called barbell horn ultrasonic technology that allows you to maintain the same amplitudes with small devices as well as large devices. A little bit more about the three examples of ultrasonic systems I mentioned. Laboratory scale system can produce about 1 liter per hour of nanoemulsion, and at a typical concentration of 50 milligrams per milliliter, that's 5,000 nanoemulsified doses of THC, for example. Bench scale BSP 1200 can produce 5 liters an hour, or 25,000 doses per hour. And ISP 3600, an industrial scale system, 100,000 doses per hour, 20 liters per hour of nanoemulsion. A little bit more about nanostabilizers. Nanostabilizer LT makes translucent liquid nanoemulsions. It's an all-in-one formulation. Anyone can use it. No R&D is necessary. It's already been done for you and put in a jar. It leads to droplet sizes of about 27, 25 to maybe 30 nanometers, depending on your starting material. The formulation is tasteless, and everything is food grade and very mild. Nanostabilizer LSO is an equivalent formulation, but it leads to the production of powders. It is organic, natural, and completely tasteless. You can make liquid nanoemulsions with it that you can then dry. The droplet size, as we measure it, is 170 nanometers or so, 170, 180. But it's likely, as I mentioned in the study, that the actual droplets that are responsible for the delivery are smaller. And that explains the data that we received, which showed that liquid and powdered nanoemulsions basically performed very similarly to each other. And with this, I thank you very much for your attention.